All right, let's get started. This is the third lecture. So we're going to continue our discussion of the center of mass. And then we will be talking about rotational kinetic energy and introduce the concept of the moment of inertia. So let's start with a brief review of what we did last time. So we defined the center of mass. All right. So So this was the definition that the position of the center of mass for a collection of particles is given by the weighted average of the positions of those particles. And the weight is proportional to the mass. So we wrote it as sum over I, mi, the mass of particle I, times ri, the vector to the position of particle I, divided by the total mass. And then there was an important property of the center of mass which we discussed, and that was the fact that the net external force acting on the collection of particles gives you the total mass times the acceleration of the center of mass. So if we add all the forces, all the external forces acting on a collection of particles, it can be a rigid body that we think of as a collection of a whole bunch of tiny little pieces. This is given by the total mass times the second derivative with respect to time of the position of the center of mass of this object or the collection of particles. So, for example, if you take a rod and throw it up in the air in some arbitrary way, it's moving and it's rotating at the same time, so it's going to do something like this. So it's also rotating, changing orientation. But if you just focus on the center of mass of this object, well, it moves like a point particle under the influence of gravity, right? So if you break up the rod into a lot of little pieces, right? So each piece is experiencing, the only external force it's experiencing is gravitational force downward. And if you add all of them up, you just get uh, the total mass of the rod times g. That's the net external force, which is downward. So as far as the center of mass at one point in the middle of this uniform rod is concerned, it's just behaving like a point particle moving under gravity, right? It's just projectile motion. It's a parabolic curve, has downward acceleration g, no acceleration in the horizontal direction. And then on top of that, now there's some rotation and that's something else that we should think about. But so we can always think about that one point behaving very much like a point particle of mass equal to the total mass of this object under the influence of the force equal to the sum of all the forces acting on this collection of particles at different positions in space. All right. Now, a special case is when there is no net external force. So a special case when this thing is zero. So you can think of a situation like this as let's say you have a frictionless table and you have a disk or some object that can slide on the surface, and you give it a kick and it can rotate around and move around. So it can be a relatively complicated dynamics after you give it a kick. But if you think about the center of mass, right? So in the horizontal direction, there are no net forces. There is no force, there is no friction. And you have normal force and gravity, they cancel out. So there are no net forces on this object. So that means its center of mass does not accelerate, right? The only thing the center of mass can do is moving along a straight line with constant velocity. So arbitrary object, let's say it has a center of mass here. As you give it a kick and then there are no external forces, well, the center of mass, the only thing it can do is move along a straight line with constant velocity. It can't do anything else because the acceleration, the second derivative of the position of the center of mass with respect to time must be zero. But the object can, for sure, rotate around the center of mass. So a little bit later, it can be, for example, kind of like here. Yeah, that's the center of mass. So it can rotate, but the center, if you think about the center of mass, it's not accelerating. And if you have an object in kind of free space, no external forces, it's just rotating around, and it's not moving, there's no transition, well, the center of mass must be fixed. That's the point in space that does not move. All right. So let's think a little bit about this question here. So you should pause the video and think for a few minutes and try to decide which one is the correct answer. All right, let's get back to this question. So you have a baseball bat that's cut into two pieces at the center of mass. So the center of mass is here. It has this kind of thicker hitting end, and it has a handle that's thinner. So we want to figure out which piece is heavier, which end is heavier. All right, so how should we think about it, right? So, on the hitting end, of course, you have higher density, right? Because it's thicker, but it's also shorter. So just from density consideration and size, it's not quite obvious. But we know that the center of mass is right there, right? So if that piece is shorter, then the center of mass is closer to the center of mass of the hitting piece. So if I just take this piece and look at its center of mass, it's almost uniform. That's just a thick end, so it's roughly in the middle here. For the handle, its center of mass is right in the middle here. And because the handle is longer, the center of mass of the handle is at a larger distance from the center of mass of the full baseball bat than the center of mass of the hitting end. So the center of mass should be closer to where you have more mass, right? And we know the center of mass is closer to the hitting end. So that implies that the hitting end must have more mass. All right. Okay. So the next topic, so we're going to switch gears a little bit and talk about kinetic energy for an object that's rotating around a fixed axis. So that's some arbitrary object. There's an axle here. It's rotating around this with angular velocity omega. So remember, if you have a rigid body, right, because all the distances are the same between all points on this rigid object, all the changes in angle are the same, and therefore there is only one omega associated with this entire object. So every point on this object is rotating with the same angular velocity, omega. So then we want to think about its kinetic energy. Right? So let's go back to the notes here. Right. So we're going to talk now about rotational kinetic energy. So we have some object, right, of some shape. There's an axis of rotation here. It's coming out of the plane, so it's rotating in the plane around this axis that's coming out of the plane. And we can always think of any rigid object as a collection of particles, right? If you break it up into a whole bunch of small pieces. So I put a grid, for example, like this. And let's say I look at one of these cells, one of these pieces. If it's small enough, I can treat it like a point particle. That's some distance from the axis of rotation, right? All right, so if this entire object is rotating around that axis, every point of it, what do you think the trajectory looks like for any point on this object? So for example, this cell, this dark cell here. Well, it must remain at the same distance r from the axis, right? Both the axis, like this point here, which is fixed, doesn't move, and this point are points on this rigid object. So their distance does not change. So the only thing it can do is to move along a circular arc. If it goes all the way around it, it's moving around the circle. But even locally, the motion is around the circular arc, right? So again, a little bit later, if it has rotated by some angle, the distance is the same. So it must be on a circular curve. And we remember from 161 that the velocity, so if a point particle is moving along a circle, it has a velocity tangent to the circle, and the magnitude of velocity is just r omega, right? To review this, basically this originates from the fact that, if let's say you have a circle, and if you consider small angle d theta here, so let's say you have your particle moving from here to here, its angle theta changes by some small amount d theta, right? So what is the length of this piece of the circle from here to here, right? We know that the perimeter of the circle is 2 pi r. 2 pi is 360 degrees. That's the full angle here. And we know that the length is proportional to this angle. So this must be r d theta. So as the particle rotates by angle d theta, the actual physical length that it moves is r d theta. And if you make d theta smaller and smaller, this curve becomes closer to a straight line, and it's going to be perpendicular to the radius, which is tangent to the circle. So therefore, the velocity, which is distance divided by time, becomes just r d theta dt, and d theta dt is omega, so that's just r omega. All right, so we have that. We know that the velocity for every little piece is r for that little piece, so r depends on where the piece is, times omega. And then remembering what the kinetic energy was for a point particle, so Kinetic energy K is 1/2 mass times velocity squared. So if that little piece has a tiny mass dm, we can write its contribution to the kinetic energy, let's call it dk, the tiny contribution from that infinitesimal piece to the total kinetic energy, we call it dk. That's going to be 1/2 the mass of that tiny piece, which is dm, times its velocity squared, which is r omega squared. All right, so now I integrate over the entire object, add the contributions of all these small pieces, and I end up with, I can factor out 1/2 omega squared, because omega doesn't depend on the position of that little piece. R does, right? So r squared remains, and we have dm here. So this motivates us to define a quantity known as the moment of inertia, I, to be equal to that integral, r squared dm. So we did it in the continuous case using an integral by dividing our object into a whole bunch of small pieces. The discrete limit of this, if you have a whole bunch of particles, so again, imagine you have like a particle here, m1, a particle here, m2, another one, m3 here. You have a bunch of point particles. And then there's some axis of rotation perpendicular to this plane. So let's say axis. And then the distance from this axis to particle 1 is r1. Here we have r2. Here we have r3. Then we can define the moment of inertia again as a sum over the masses of these particles times their corresponding distance squared. So these r's are the distance from the axis, right? If I draw this in 3D, so let's say that's the axis of rotation here, it's a line that's coming out of the board. So let's say mass m is somewhere here. You can draw one line kind of perpendicular to this axis, which hits the axis, and that's the distance. If you have another mass in a different plane, for example, if you're thinking about a three-dimensional object, you're going to get a different distance, which is measured in a different plane. So that's the definition of moment of inertia. And then, of course, what happens is that the total kinetic energy is 1/2 I omega squared for an object rotating around a fixed axis, and I is the moment of inertia around that axis. So if we think about this table that we started talking about in the beginning of the course, we had like maybe position and angle as an analog. We had maybe omega and velocity and angular velocity. Angular velocity was the rotational analog of velocity. Here we see that the role of mass is played by the moment of inertia in the sense that the kinetic energy for linear motion is 1/2 mv squared, and for rotational energy it's 1/2 I omega squared. All right. So this is the expression we just found. This sum over masses times distances squared is the moment of inertia of the object, and the rotational kinetic energy has this expression 1/2 I omega squared. The units, as you can see here, you have masses times length squared. So it's going to be kilogram times meter squared. Importantly, it depends on the axis of rotation. All these distances were measured from the axis of rotation. It's a quantity that's defined for an object and an axis. It's not just uniquely determined if you know what the object is. And as you can see, masses that are farther from the rotation axis contribute more to the moment of inertia because of that factor of r squared, distance squared. This is not a new form of kinetic energy, right? We just broke up this object into a whole bunch of little pieces. We looked at the instantaneous velocity of each piece, and we just added regular kinetic energies. But we ended up with this expression that only depends on angular velocity for a rigid body and the moment of inertia. So it's a very convenient expression. All right. So that's the continuous limit that we already talked about. So this is a table for a whole bunch of continuous objects that lists their moment of inertia for rotation around, again, some given axes, right? So here you have a rod rotating around an axis that goes through its center, a rod rotating around an axis that goes through one endpoint, slab, again, the end, the center. You can have a cylinder, a filled cylinder, or a disc around its center, a cylindrical loop about the center, solid sphere about the axis that goes through the center, or a spherical shell. So dimensionally, of course, there's only one length scale in all of these. So you're going to get r squared because we need some length squared, and there's the mass, total mass of the object, and there's going to be some numerical coefficient that depends on the geometry and how the mass is distributed inside this object. All right. Let's think about a couple of these. So let's pick thin rod about end and cylindrical loop about center. Let's find these results using the expression that we have for the moment of inertia. Calculating the moment of inertia. All right, so the first example is extremely simple. So let's say a loop around center. Okay, so if I divide this loop into lots of small pieces, we immediately see that, so let's say I take one piece over here, say it has a mass dm. Well, all these pieces, if the radius is r, are a distance r from the axis of rotation, right? They are on a circular loop, so this other piece is also a distance r. So if I look at the integral r squared dn, which is the moment of inertia, well, small r for all of these small pieces is capital R that doesn't depend on the piece, doesn't depend on where that piece is. So this just factors out of this integral, and then I have the integral dn. So adding the mass of this little piece, all these little pieces, that should give me the total mass of the loop. So that's it. There is no coefficient. The moment of inertia is total mass times r squared, because all the mass is the distance capital R from the axis of rotation. So let's say a thin rod around an endpoint. So that's my rod. This is the axis. Again, imagine it's coming out of the plane. You can rotate like that around that axis. All right, so again, it's the same strategy. I need to divide it into little pieces such that each piece, we can approximately say it's at one distance from the axis of rotation. So I look at a tiny piece over here. Let's say it's a distance r from the axis, and the length of that piece is dr. Okay, so let's say the length is again L and mass is m. So first I need to find the mass dm of that infinitesimal piece that has length dr. Well, we did this already for the center of mass, right? It has uniform density, so the linear density mass per length is m over L, and then we multiply that by the length of that small piece, so we get m over L times dr. And let's now write I is equal to integral r squared dm, which is the integral r squared m over L dr. And then these pieces are part of the rod. So r starts here from 0, goes all the way to L. For any value of r between 0 and L, we have a piece that belongs to this object. And there are no pieces for other values of r. So that gives us the limits of the integral. So it's an integral from 0 to L. So m over L does not depend on r. We factor it out. R squared dr. Integral of r squared is r cubed over 3, right? You take the derivative of r cubed, you get 3r squared, so that 3 cancels this 3, and the derivative of r cubed over 3 is r squared. And this we calculate from 0 to L, so for 0 it's 0, for L it's L cubed over 3, so m over L, L cubed over 3, which is 1/3 mL squared. So that's our second example from this table. There's no need to memorize the expressions in this table. We can always look them up. Maybe it's worth it to do another one. Maybe let's do the disk as well, so you see a more kind of complex geometry. So let's do the disk. So this was one example here. We did a loop, we did a thin rod. So a disk around center. All right, so here we have to be a bit more careful. So we can, of course, like work in Cartesian coordinates, break it up into like a grid of tiny pieces of kind of dimensions dx, dy that are at position xy, but that makes it really complicated. We can make use of the symmetry, right? So this thing has this angular symmetry, and it's very convenient to break this disk into a whole bunch of rings. And we already know the result for a ring. It's just the total mass times this times radius squared. So if you break this filled circle into a whole bunch of circular loops, that's another one. All right, so if you look at one of these, let's say you look at one of these loops that has a thickness, again, dr, and has radius r. Well, the only thing we need to do is to find its mass, right? What is the mass of that tiny loop, infinitesimally thick loop there? Well, again, it's a disk with uniform density, right? So the mass of this loop is the surface area of the loop, which is a tiny surface area, times the total mass divided by the surface area of this circle. So let's say the circle has the radius capital R here, and mass m. So kind of the surface density, mass per unit area for this circle is going to be m over pi r squared, right? Pi squared is the area of the full circle. And then we have to multiply that by the area of this little loop. So this little loop has length 2 pi r, right? So the length of this curve is 2 pi r. And then it has a thickness dr. And dr is always perpendicular to 2 pi r. So the sums of these pieces along the circular arc will be 2 pi r, and each of them is multiplied by dr, right, to get the area. So the area is going to be 2 pi r dr. Okay, so now we're in business, right? So we have an expression for the mass of this element. We picked an element whose moment of inertia we already know, or is simple to find. And then we can write I as, again, integral over the object. So once we connect it to geometry, then we can put the bounds of r squared dm. Now this is going to be integral r squared. Let's clean up this expression a little bit. So we have, in fact, the pi's cancel out. We have 2m over capital R squared. And then there's another r dr. So now that it's an integral dr, we can ask ourselves, where do we have these loops? Well, we have a tiny one at r equals 0. We keep having them for all r's up to capital R, and there's no mass outside the disk, so the integration range will be 0 to r. Okay, so we factor out 2m over r squared. We have integral from 0 to capital R of r cubed dr. That gives me r to the 4th over 4, which is 1/2, right? 2 over 4 is a half. R to the 4th over r squared is r squared, mr squared. So this was a bit more advanced. You won't need to do calculations like this, but it's helpful to see how some of these expressions are found. So again, yeah, we found the correct result there. All right. Let's do also an example with discrete masses. So again, similar to the center of mass, we have continuous cases where we find the center of mass with an integral. There are these continuous extended objects where we find the moment of inertia by doing an integral. And then there are cases where you have just a bunch of discrete point particles and you want to find the moment of inertia or the center of mass, so we use the discrete sum. Okay, so let's do this example here. Find the moment of inertia around an axis going through mass m3. And the axis is normal to the plane. So we have an xy coordinate system. We have a mass m3 here, which is 2 kilograms. And this distance is 1 meter. Have a mass m1 here, that's 1 kg, sitting at the origin, and let's say a mass m2, again this is 1 meter, and that's again 2 kilograms. So we have an axis coming out of the plane here, where mass m3 is. So we can think of this as a system made out of 3 point particles connected with massless rods, if you want to think of it as a rigid object. All right, so we want to find the moment of inertia around this point, around this axis. So pause the video, try to work this out using the formula, and then we'll come back to the video and go through it together. All right, so let's see. So first we have masses, right? M1, we have 3 masses. M1 is 1 kilogram. M2 is 2. M3 is similarly 2 kilograms. Now we want to find the distances for each of these masses to the axis of rotation, right? Remember, our general formula was sum over all the masses times their corresponding distance to the axis of rotation. So for M3 it's easy, right? The axis is going right through it, so there is 0 distance. So R3 I know is 0. For M1, the distance is given us given to us directly, right? It's m1 is here, the axis is here, perpendicular to the board. So 1 meter is the distance between the mass and the axis. So R1 is 1. What about the distance between this mass m2 and the axis of rotation? Well, we have to do a little bit of geometry, right? So what is that distance? So if that's m3, that's m2. R2 is the length of this line, right, connecting these two masses. So we know that from here to here we have 1 meter. From here to here we also have 1 meter. So if I look at this right triangle, I can write R2 squared is 1 squared plus 1 squared. So that's 2. That gives me R2 is square root 2 meters. Okay, so we now know what that is. Now let's just plug it in. So we find I to be m1 times r1 squared is 1 times 1 squared. m2 is 2 times square root 2 squared plus 2 times 0 squared. So that gives me 1. Square root 2 squared is 2. 2 times 2 is 4. So that's 4. And that's 5. 0 is 0. So that's 5. And the unit's kilogram meter squared. Okay. So that was a problem involving discrete point particles finding the moment of inertia for a given axis. What about if we try to find the moment of inertia around a different axis? So now find I around an axis going through M1. Okay, so again, I can draw this. I have M1 here, M3 there, M2 there. Now distances change, right? So now R1 is 0 because the axis is going through M1. R2 is going to be this distance from here to here. That's 1 meter. R3 is similarly from here to here, from M3 to the axis, which is 1 meter. So the masses are the same, the distances change because I moved my axis to a different location. So now I find my moment of inertia to be m1 times r1 squared is 0, m2 was 2 kilogram, m3 was 2 kilograms, so I get 2 times 1 squared plus 2 times 1 squared, and that's 4 kilogram meter squared. So this is an explicit example where we see for the same system, for the same collection of masses, we have a moment of inertia which depends on where the axis is, right? So those lengths are measured from a given axis. Okay, so now that we've had some practice with finding the moment of inertia and center of mass, it's worthwhile emphasizing how they're different, right? See, the center of mass is a point in space which we represent by a vector. If you fix a coordinate system, to find the position of the center of mass, or to find the center of mass, to find where it is, we have to find a vector, right? So we had, let's say, RCM is sum over I mi Ri divided by the total mass. So we're adding some vectors. In 2 dimensions, it has an x component and a y component. In 3 dimensions, it has an x component, a y component, a z component, right? And it's just a property of the object, right? It's somewhere with respect to that object. If you just fix your coordinate system, you find where the center of mass is, and then with respect to kind of the distances between the center of mass and all points of the object don't depend on your coordinate system. So let's say I have a coordinate system, I fix it, I have an object, I find the position of the center of mass here, then, okay, so maybe there's some vector to one point on the object, there's another to the point to the center of mass, but these distances are just fixed, right? So it's somewhere on the object, and it's a vector. Moment of inertia, on the other hand, is a scalar, right? There is no vectorial thing. These r squared is just the length squared. It's the length of the line connecting the point to an axis. So we have an axis, first of all. It's defined with respect to that axis, and then, you know, we have M1 here. We have to draw a line perpendicular to the axis, which hits the axis, and find that distance. Similarly, for a different mass over here, the masses could be in different planes, but the quantity we find is a number. There is no direction associated with moment of inertia. So these are some of the differences between the two. All right, so I think that's a good place to stop. So we defined the moment of inertia. The motivation was that it's a quantity that's kind of the analog of mass, right? If you have an object that's rotating around the fixed axis, the kinetic energy is 1/2 I, the moment of inertia, omega squared. And we had some practice finding this quantity for discrete and continuous cases.